Let t sub 0, t sub 1, t sub 2, and so on be defined by the formula t sub n equals 2 plus n for every integer n greater than or equal to 0. Show that this sequence satisfies the following recurrence relation for every integer k greater than or equal to 2. T sub k equals 2 times t sub k minus 1 minus t sub k minus 2. Now, we don't need to use mathematical induction here because we don't need to use p of k to prove p of k plus 1. In this instance, we can simply prove p of k is true for all k greater than or equal to 2. And we'll do this directly. We'll start the proof by saying let k be an arbitrary integer with k greater than or equal to 2. We're going to show that this recurrence relation holds by evaluating each side of this recurrence relation separately and utilizing this explicit formula. So let's start with the left-hand side. Now, since k is greater than or equal to 2, then k is greater than or equal to 0, and that's the inequality we need to satisfy in order to utilize this explicit formula here. So this means then that t sub k equals 2 plus k. Now let's handle the right-hand side. We'll evaluate the right-hand side using the same formula. But before we do that, we need to justify whether we can actually use this formula. Now, since k is greater than or equal to 2, we can subtract 1 on both sides to get k minus 1 is greater than or equal to 1, which is still greater than or equal to 0. And that's what we need to show, that k minus 1 is greater than or equal to 0, so that we can apply the explicit formula to t sub k minus 1. But we could also take this inequality here and subtract 2 on both sides. So k minus 2 is greater than or equal to 0. Either way, k minus 1 and k minus 2 are both greater than or equal to 0, so we can apply the explicit formula for the right-hand side. So 2 times t sub k minus 1 minus t sub k minus 2 is just 2 times, and then by the explicit formula, this would be 2 plus, instead of n, it would be k minus 1, and then minus t sub k minus 2, which is just 2 plus k minus 2. And we can simplify this by dropping some of the parentheses, but not all of the parentheses. Some of these parentheses will simplify and distribute before we just drop them. So first we can simplify these parentheses to 2 times k plus 1 minus, and this is just k. And then we can distribute the 2, so this is 2k plus 2 minus k, which is the same thing as k plus 2. And if you notice, whether we evaluate the left-hand side or the right-hand side, either way we end up getting 2 plus k. And so this means t sub k equals k plus 2, which equals 2 times t sub k minus 1 minus t sub k minus 2. But that just means that t sub k equals 2 times t sub k minus 1 minus t sub k minus 2. Now, the important thing about this proof is that k is arbitrary. So k could have been 2, it could have been 3, it could have been 4, and we can go through this proof to show that this recursive definition holds. And so this proof is a generalized version of that. We're not just checking k equals 2 and k equals 3 and k equals 4. We're setting k as an arbitrary integer, and it's the arbitrariness that allows us to extend this proof universally to all integers greater than or equal to 2. Thanks, everyone, and I'll see you in the next video.